Okay, I'm going to try making this video again. I tried doing it last night and the video froze up. So we're going to start off by going over the last derivative formula that we've covered in the last two sections, differentiating y is equal to the log base a f of x. So what we're going to do with this to start is I am going to use the change of base formula to rewrite log base a in terms of log base e. So to do that, I'm going to take the natural log of the argument f of x, and then we're going to divide that by the natural log of our original base a. Okay, so I then am going to rewrite this as 1 over the natural log of a times the natural log of f of x. And then we're going to differentiate both sides implicitly with respect to x. So the derivative of the left-hand side is just going to be y prime. The derivative of the right-hand side, I can pull the coefficient 1 over the natural log of a out front. And then when I differentiate the natural log of f of x, that's going to be 1 over the argument, f of x, times the derivative of the inner function using chain rule, which is f prime of x. And then I'm just going to reorder the factors. So y prime is going to be equal to, when I multiply these two fractions, I'm going to get 1 over f of x times the natural log of a in my denominator, times f prime of x. And that right there is your derivative formula for the log base a of f of x. Okay, last set of examples we're going to work on is going to deal with this process called logarithmic differentiation. All right, so we'll do 2 examples on this video and then the third example on another video. So directions here say to find the derivative of the function. For number 1, we have y is equal to x raised to the x power. So hopefully you're looking at that function thinking, okay, I don't have any rules that allow me to take a derivative of a function of that type. Like if we had the function x raised to some numeric power, like x raised to the second power, we could use power rule to differentiate that. That is whenever we have x raised to some numeric power. Here we have x raised to a function power. This is also not an instance of like differentiating an exponential function, because with exponential functions you have a numeric base raised to a function power. Okay, so we can't use those rules in this instance either. So what we're going to do to differentiate a function of this type is logarithmic differentiation, where we are going to take the natural log of both sides of our equation. And then when I take the natural log of the right-hand side, I can now pull this power out in front of the natural log as a factor. So this is going to give me the natural log of y equal to x times the natural log of x. And now we have this equation written in a form where we can differentiate, differentiate implicitly. So the derivative of the left-hand side is going to be the reciprocal of the argument, 1 over y, times the derivative of the inner function, y prime. And then to take the derivative of the right-hand side, we are going to use product rule, which is the derivative of the first, 1, times the second, the natural log of x, plus the first x, times the derivative of the second, which is 1 over x. So we get 1 over y prime equal to the natural log of x plus x times 1 over x is just 1. And then if we want to isolate y prime, we need to multiply both sides by y. So we get y times the natural log of x plus 1. And you would think that you would be done if we implicitly differentiate both sides, but if we look at our initial function to start with, we have y written explicitly in terms of x to begin with. So when we find the derivative, that derivative had better be written explicitly in terms of x as well. So that means that I can substitute x raised to the x power in the place of y. So we get y prime equal to x raised to the x power times the quantity, the natural log of x, plus 1. All right, and that is our derivative using implicit differentiation. Okay, I want you guys to give number 2 a try. So you have y is equal to x raised to the power of rad x. So go ahead and pause the video to work this one out. And then whenever you're done, you can unpause and then we'll work through the explanation together. All right, so we have the same situation that we did in the previous example. We can't differentiate x raised to the x power using like our standard differentiation rules. So we're going to logarithmically differentiate this, taking the natural log of both sides. When I take the natural log of the right-hand side, I can then pull rad x, the exponent, out front as a factor. Okay, so now we have something that we can differentiate implicitly. So the derivative of the left becomes 1 over y, y prime. Again, when I use product rule to differentiate the right-hand side, the derivative of rad x, whenever I simplify, is 1 over 2 rad x times the second function, the natural log of x, plus the first function, rad x, times the derivative of the second function, which is 1 over x. So we get 1 over y times y prime equal to the natural log of x over 2 rad x, plus rad x divided by x is going to simplify to 1 over rad x. And then on the right-hand side, I want to combine into a single fraction, getting a common denominator. So my common denominator is going to be 2 rad x. The first fraction has that denominator, so I'm going to leave the numerator alone. The second fraction, I have to multiply the numerator and denominator by 2. So we get 1 over y times y prime equal to that expression on the right-hand side. I can then multiply both sides of the equation by y. And then lastly, y is written explicitly in terms of x at the start, so our derivative needs to be written explicitly in terms of x as well. So we're going to replace y with x raised to the rad x power. And that right there is our simplified derivative for the given function. Okay, so there will be one more example of logarithmic differentiation on the next video, and that'll wrap this lesson on derivatives of log functions up. Okay, we'll see you guys in class tomorrow. Take care.